So, the kind of examples we saw the kind of examples we saw scheduling or segmental least square, we had polynomial time algorithms. If you do a recursive formulation then and you do a recursive algorithm, it gets you exponential, but we broke it up into sub problems and did some tabulations and got a polynomial time algorithm. Today we look at examples where these are hard problems. We don't expect polynomial time algorithms, but we are going to use dynamic programming to design better exponential time algorithms than standard naive exponential time algorithms. Okay. So, let's start with the set cover problem. You've seen them all in the summer class. Yes. So, what's the problem? You have a universe without loss of generality. Let's say it's an n element universe, and you have a family of sets so it will be like some S1, S2. And what is the goal? This is the input. Find the minimum sized subfamily of F let's call this F prime. So, you want to find some small collection of subsets from this family which together cover my universe. This is an NP-hard problem. I mean, you all probably know already what NP-hard means, and it models a lot of natural problems like vertex cover, dominating set, and so the best you can hope for is an exponential time algorithm. So, what would be a brute force exponential time algorithm? Right, all subsets of F, because the solution you are looking for is a subset of F. Try all possible subsets of F, which gives you a family of subsets. Take their union and see whether that covers you, and pick the one which is the minimum sized. And so, how much time will that take? Right. So, this is like order 2 power m times some n power c or something, because you are just looking at the union of the sets in the family. Yeah, maybe even m to the c for all you care. It could have up to m sets, just take their union, see whether it covers the entire set. Now, m typically is much larger than n. So, yes, granted you have to live with exponential time algorithm, but do we really need 2 power m, and can we improve that to 2 power n is the question. Okay. And we will show that it is indeed possible using dynamic programming. So, let us see how I would use dynamic programming, right. When we saw the examples last time about some choice we make, and then that tells you the sub problems to solve, right. Some sort of a choice I am going to make, which tells you, okay, if I pick this, I have this, if I don't pick this, I have this, and then I have, then that just throws open the sub problems, and then you are fine, right. So, what sort of choice would you want to make? Whether you want to choose S1 or not, pick any set. It turns out here it's convenient to look at SM. Okay, doesn't, I think S1 should also be fine. But let's try SM. So if so, let's write down that I'll have to give some symbol. S, the set cover I am looking for of M U. This is 1 to M, right. This is the minimum number of sets from F needed to cover U. Okay. So, if SM is in the solution, then SMU is what? Can you write a recurrence? Yeah. U minus SM, because now what you want to cover, yeah. See that? So, what? So, suppose I pick SM into the solution, I am talking about how many sets do I need to cover the universe. So, I picked one set SM. Now, what is left to do is to cover my universe minus SM, because SM is a set of elements, it already covers some elements of the universe. So, subtract that and using 1 to M minus 1. Okay. If SM is not in the solution, SM minus 1, then use 1 to M minus 1 to cover the set U, right. This is it. Okay. Now, you have to be careful, what are the sub problems we have. To compute SMU, I need SM minus 1, okay, and some other subset of U, right. So, my more general version of the problem I will be talking about is, so more generally, what are the sub problems? S I comma U prime, where I have 1 less than or equal to I less than or equal to M, and U prime is a subset of U. These are the sub problems I need, right, because when I want to compute SM, it requires SM minus 1. So, that is the first term, and then it requires some other subset of the universe. And what is SI U prime? From, okay, so we do not know whether SM is in the solution or not. So, what do you do? Minimum of this, because it is a minimization problem, right. Right. So, SI U prime is minimum of S I minus 1 U prime and 1 plus S I minus 1 U prime minus S I. For I greater than or equal to 2, if I want to compute SI U prime, What are the things I need? I need S I minus 1, the previous one, for all subsets. I do not know what this, either u prime or u prime minus S I. And what is S 1 u prime? That is a base case, right. So, whole thing about dynamic programming is coming up with some sort of a recurrence like this. Recursive formulation tells you what are your sub problems. To compute an intermediate stage of the sub problem, you can compute it from the previous values, then you need a base case. So, it is S 1 u prime. So, I will give infinity or something, right, because we are, it's a minimization problem. It is 1 if S 1 contains u prime, right, because you want to cover u prime with only S 1. So, if S 1 contains u prime, it is 1, otherwise it is infinity, because it is a minimization. So, some other guy will take care of it. That is it. Now, let us see how much. So, that is a complete algorithm, right. You can write a loop, and if you really want to know what are the sets you want to include, then you also capture whenever whichever is minimum. If this is minimum, then you know that you are picking Si, and otherwise you do not pick Si. Okay. And how do you compute the running time? First, figure out how many different sub problems are we computing. Number of table entries, let us say, right. This is a sub problem. How many? Mn. U prime is an arbitrary subset of U. This tells you, this is it, right. You look at the indices and that tells you. Number of subsets is m, but you are computing this for arbitrary subset of U, because what you are going to, you need U prime minus Si, which is some arbitrary subset of U. So, you are computing, this tells you Si U prime for any arbitrary subset of U. Can I cover it, or how many sets do I need to cover? How many sets do I need to cover that using 1 to I? So, the number of sub problems is 2 power n times m, and time for each entry it is just this, right. To compute Si prime, either you pick Si minus 1 U prime, which is sitting there, or from U prime you have to sort of subtract out Si. So, that is some order n time, universe size time, the worst case, and then another table entry. So, I am going to say it is order n. So, overall better than 2 power m we were looking for, or the brute force was. For the most general version of set cover, I don't, this is the best we know. I don't think you can improve, at least so far we do not have an algorithm better than this pretty much. But if you have some assumptions on the sets, families, maybe you can. So, pretty simple dynamic programming, it just gives you a big lift in the running time, and all you have to do is just take your choice, do I want to include one set or not, right, and that Once you make that choice, then you have a recursive formulation. It tells you what sort of subproblems you need and what is the order in which you have to compute these subproblems and what is the base case. That's it. Okay, very simple. Okay. This is like a covering problem. Okay. The other problem we want to look at is this traveling salesperson problem. What's the input? You have age weighted graph. Let's even say it's complete. Right? So, I have a complete graph. Every age has a weight which is non-negative weight which corresponds to the distance. And what do you want? The output is min weight Hamiltonian cycle. Again, an NP-hard problem. For the most general version, you don't expect polynomial time algorithm. What is a brute force exponential algorithm? N factorial, right? Try all possible permutations of 1 to n, more like n minus 1 factorial, because it's a cycle. Then you just go and check whether every adjacent one is an edge, compute the total weight, compute the minimum among them. So, that is like an order n factorial, more or less. That is sort of the running time. And we want to improve it using dynamic programming, and improve it meaning get a better exponential time algorithm. Okay, so let's look at the Hamiltonian cycle. I mean, let's fix on one vertex 1. Here, the choice I'm going to make is what is the vertex before me. So, this is the Hamiltonian cycle, and what is this vertex which is before me, and so again, let's say so this length of this path can be written as length of the shortest path starting at 1 ending at V, visiting all vertices of V minus 1 exactly once. So, in a sense this, so suppose the Hamiltonian cycle ends at V, right, this is my choice, then this path is the shortest path satisfying this condition, starts at 1, visits every vertex of V minus 1 exactly once and ends at V. Okay. I need the ending point because I am going to put things together, different parts are going to be stitched. Okay, so let's write. So this is now like this kind of a notation. This is my notation. Let's write this in a recursive form, and then we are in shape. Okay. So what am I looking for? What kind of a running time I'm looking for? Instead of all permutations, I want to look at all subsets somehow. Okay, and then I get a 2 power n kind of a running time. Okay. So now let's make this. I mean, the next choice is who is the vertex before V, right? So I would say C V minus 1. So it should start at 1, end at, so always starting at 1. Okay, like we are going to fix that vertex. Somehow you're starting at 1, and where do you end is your question. And you want to end at V, visiting every vertex of V minus 1 exactly once. Look at the previous vertex, then what? What is it? It is end at U. So I want to start at 1 and end at U. So that's a symbol. Plus exactly. Plus edge UV, right? The distance UV. So now it says start at 1, end at some vertex U, visit everything other than 1 and V exactly once, and among all such paths take the minimum one, because you sort of all permutations is somehow built in here, plus UV, because you want to end at V. So now what are the sort of the sub problems? The sub problems are you a vertex here and this is a subset which you want to visit, right. So that suggests the sub problems. Let's write more generally what the sub problems are. Let's say CVS length of the shortest path from 1 to V, visiting every vertex of S exactly once. So V is some vertex in V minus 1 and V is also in S, and S is some vertex of V minus 1. You want to start at 1 and then you want to end at V. Now I am going to say visit some subset completely, and then end at V, some subset, because as you move on you are going to be visiting some subsets. So I want the end point to stitch it with the next path. So now let's write the recurrence for CVS. CVS is equal to minimum of C. So let's say I want to start at 1, then visit all of S and end at B. So now I come back to this U. So C U S minus B plus C distance U V, where U is in S minus V. So some vertex in U S minus V is what the previous vertex would be. So I start from 1 and end at that vertex U, visiting everything in S minus V exactly once, and then you do U V. This is it. So what is my output? What do I want? Start at 1, end every vertex of V minus 1 exactly once, and end at 1. Starting vertex is 1 forever, right? That is how our notation is, right? It is always from 1, some canonical vertex which we have fixed. So start at 1, visit everything other than 1 exactly once, and end at 1. This is what we want, and that is it, right? So this tells you how many subproblems you are going to compute. Okay, is there a base case? Yeah, base case is S is empty, C V empty, or is it? No, maybe not. No, your S V should be in S. So some singleton. Let's call it some singleton. That means, so if x is equal to V, then it's simply distance of 1 comma V. Right? I want to start at 1, end at V, visit every vertex of this set exactly once. And if x is otherwise, it's infinity or something. Actually, I mean the problem is not even defined, because I want to assume that V is an S. Okay. So this is the only, yeah, we could define it in case I need it for a subproblem. I can define it infinity. Okay, so somehow breaking this permutations into subsets, you figure out how you start. It takes us to the subproblems. We know how to write the recurrence for the subproblem. Where do we start? This is the base case. Where do I want to end? That's so. What is the order in which you're going to compute this? In increasing order of the set sizes, because you start with singletons, and then for a larger set, when I want to compute, I should have computed for smaller sets. That's all I needed. Right? So how much time does this take, and how many number of table entries? Time for each. Sorry, n into 2 to the power n, right? That's not very clear. You need to sort of. I mean, S is contained in B minus 1, so it's like 2 power n minus 1. That's the only. Yeah. because you do not know what set you are going to get. Yeah, so 2 power n minus 1, and this is also n minus 1. So, it is like order n in 2 power n, and what is the time for each? It is here. To compute one entry, how much time do you need? The complete graph. No, it's a min over some n quantities, right? Yeah, this is all in the table. That's the whole point, right? So, it's n. So, overall it's 2 power n square, improving from brute force. Yeah, and as always, if I really want to find the cycle, then you remember this u which minimizes it. So, then it tells you what is, you want to end at v, what is the one vertex before that, and then C u s minus v. So, for every pair, you remember the u that minimizes it, right. So, ultimately I want 1 v minus 1. So, if you find the u that minimizes it, that is the vertex before, that is the one before that, because I am going to start at 1 and end at 1, and the one before that I will know from that variable. Then you compute C 1 v minus v ending at v, sorry, C v v minus 1 end at v, what is the one previous vertex, and that tells you u. So, you can get all the vertices, right. You just have to compute this. When you are computing this minimum, just remember the variable that realizes the minimum, right. Okay. It is tricky all the time. It is tricky all the time. So, that is where all the work is, right. So, it is yeah, it's just practice. I mean, it's not obvious all the time. Okay, so I mean, that's why I'm going slow to see whether we can see. So let's look at graph coloring problem. So you're given a graph, undirected graph. And we are interested in the chromatic number of graph. And what is chromatic number? What is, so you want to color the vertices, right? So, so it's a function from vertex set to some k. So you can, yeah. Let's ask the question: is the chromatic number less than or equal to k? Then you want, can you color the vertices 1 to k such that for all I j in E, f of I is not equal to f of j. You want to color the vertices with at most k colors, so that whenever there is an edge, the endpoints get different colors. So, set cover is a covering problem, TSP is a permutation problem, and this is a partition problem. So, what would be a brute force algorithm for this? Right, because it's not a subset, it's not a permutation problem. You want to color the vertices with 1 to k such that this property is true. So, if you want to really try all possible things, then give up to k colors for each vertex. So, number of different possibilities is k power n, because each vertex gets k choices, and then for each of them you check whether this condition is satisfied. So, that is like a k power n, and particular if I want a minimum chromatic number, even if k is not given to you, you just have to try different values of k, right. So, if k is 50 colorable, then this is like a 50 power n, because you just go 3, can you color it with 3 colors, 4 colors, 5 colors, and eventually you will, the first time you are going to get an S is when you stop. Now, using dynamic programming, you can improve it substantially. Now, let us see how do you break it up into problems, right. So, can you think of a recursive formulation, right. So, what is a color class? Yes, and they have to be independent, right, because subset of vertices that get the color class. So, one brute force thing is that try all possible subsets or independent sets, and I say, okay, I am going to color this subset one color, right. Now, what is left is now optimally color the remaining vertices, the remaining graph, right, with completely different colors. So, I can just delete it. This is one color class, I am going to delete it, and the remaining one you just color in whatever way you want. But it is not clear maximum independent set is necessarily a good idea. Yeah, some independent set. He was saying, should we just find a maximum independent set and throw it? It is not obvious that every color class is maximum independent set. Okay. But okay, but let us keep that thought. We will come back to it to get a slightly better algorithm. For now, let us say we pick some independent set, right. So, here is a recursive algorithm. For every independent set S contained in B, chi of G, or try all possible ones and then pick the minimum, right. So, it's 1 plus chi of g of B minus S. This is the induced subgraph on B minus S. And who try over all possible. So, the property we are simply using is that a color class is an independent set, and the fact that once I color, so this is this optimum substructure property, right. Once I color one independent set with a color, then this must be an optimum coloring of the remaining graph, right, because if there is a different way of getting a better coloring, use that plus 1 and you will get something better. And color class is an independent set. So, what are the sub problems now? Induce subgraphs, because this is what I need, right. I need independent set is something I run through all possible subsets, right. And what once I have that, then I want the optimum way of coloring the remaining subgraph. So, try all possible subgraphs, find their optimum coloring and just build it bottom up, right. So, I want the chromatic number of a subgraph, right. The subgraph is determined by a subset of vertices. And what is this quantity? We know it's min over all S prime contained in S. S prime is independent 1 plus what is the output I want? The entire vertex, so this for this whole graph, and the base case would be single vertices and you can just color that vertex 1. Oh, because this is all new colors. Always we are coloring with new color. So, we don't, so we take an S prime, color it with one color. Now, whatever the number of colors you need to color the remaining, they are all separate colors. That is why I add 1 plus, otherwise I won't add 1 plus, right. Okay. Now, let us do this. First, let us do a brute force kind of thing and then we will do a tighter analysis of this. So, how many 2 to the power n, right, because this is it, right. That is all our sub problem. For every subset, take the induced subgraph. So, that is like a 2 to the n, and time for each is this, right. Looking at all subsets of that vertex set, and then this is a table entry. We are going to pick them up and do a min. So, the number of subsets could be another 2 to the n brute force. So, it is still better than our k power n for k is very large. But this can be slightly improved with the tight analysis, because the number of subsets is not always 2 power n, right, because initially as you have smaller and smaller sets, the subsets are not 2 to the n, right. So, how do I tightly, I want to combine both of them. And so, for example, if I have if S is a I element set, then what is the running time for that? 2 power I, not 2 power n, right. So, this builds. So, but how many I element subsets are there? N choose I. So, here is my tighter analysis. For every number of I element subsets is n choose I. For every I element subset, that running time is 2 to the I. Run this over all I, is it 3 power n, right. This is binomial 1 plus 2 whole power n. So, this is again nice, just dynamic programming, and fact that one color class is an independent set. So, okay, this can be improved by doing the following. Now, you mentioned about maximum independent set, right. Now, that is not obvious that if you have a coloring, then the optimum coloring would make the color classes are maximum independent sets. That's not necessarily true. But what one can show is that at least one color class is a maximal independent set. Okay, let me just there exists an optimum coloring with one color class maximal independent set. This is not hard. So, how can I, so suppose somebody has given me an optimum coloring, okay. So, this is my color classes. Now, I claim that at least one color class, let us say my favorite one, I can make it a maximal independent set. What is a maximal independent set? That it cannot be expanded to add any more vertex. Suppose I have a, suppose this is not maximal, right. Now, I can, that means there is some vertex sitting here, which I can add to this independent set. Let me pick that and add it here. That means I am going to recolor it. It might be sitting in one of this, it was colored some other color. I am going to take that and put it here and color, give this color. It does not change anything about the number of optimum number of colors. And I can keep doing it, right. I can just find any vertex which I can include to this color class. Now, simultaneously I may not be able to do this for all color classes, because then there may be some conflict, right. I am trying to bias towards this. I want to make this a maximal independent set. So, I will pick arbitrary, any vertex which I can include into this without violating this independent set, just pick that from whatever color class it is and put it here, which means I am just recoloring that vertex, it comes here. Okay. So, that's the proof of this observation. There exists an optimum coloring. So, given an optimum coloring, I can do some local changes to get an optimum coloring with at least one color class a maximal independent set. So, now how does that improve my running time? Because now I can say S prime is a maximal independent set. So, do not run over all possible independent sets, run over all maximal independent sets, and take that and give one color class and then recursively color the remaining graph. Okay. Okay. How does that improve? Now, it turns out you can prove that in a graph on n vertices, the number of maximal independent sets. Okay. In fact, at most 3 power n by 3. You can't actually have 2 power n maximal independent sets, but you can have as large as 3 power n by 3, which is better than 2 power n, because right, it's cube root of 3, that's like 1.44 or something. Okay, because if you want too many maximal independent sets, the graph has to be very sparse. But if what is the sparsest graph? Well, there is no edge at all. That has only one maximal independent set. Okay, so there is some sort of a balancing thing. So, what is a graph where there is so many independent sets? Look at the following graph. Okay, so there are n by 3 triangles, that is my whole graph. What is a maximal independent set in this graph? Yeah, so you pick one vertex from here, one vertex from here, one vertex from here, any of them. That I mean, you can't omit it. You have to pick exactly one from each. Because if you didn't, that's not maximal. There are 3 choices, and there are n power 3, n by 3 triangles, and that's sort of the maximum. Okay. No, so this is one example where this is achievable. That does not prove that this is maximum, I agree. So, that requires an argument. So, the argument is actually sort of a recursive thing. One can so, okay, how do you prove this? Do I remember it? So, what I do is let's say I pick one vertex into the independent set. Okay, then I immediately exclude all its neighbors, right. So, yeah, so here is okay, let me write another observation here. The vertex or any of its neighbors must be in any maximal independent set. Pick any vertex, any of your favorite vertex, and look at its neighbors. I claim that in any maximal independent set, Either the vertex or one of its neighbors must be there. Why? Because if none of its neighbors is there, and then what stops you from putting this vertex into that set? You are looking for a maximal independent set. So, none of its neighbors is there, you can jolly well add this vertex into that set and get a maximal independence. So, either a vertex or any of its neighbors must be there, right. So, now suppose I pick a vertex, I pick some vertex x. Now, I want to count the number of maximal independent sets, right. So, let us call this as m of n. I want to show that m of n is at most this, right. This is the number of maximal independent sets. Let us just pick some vertex, and what are how many choices I have, either a vertex or any of its neighbors. Let us say it's that vertex degree is d, then I have d plus 1 choices, right. And then it recurs once I pick a vertex or any of its neighbors, I have to throw them out into the remaining thing. So, it will be T m of n minus t minus 1. This is it, just solve this recurrence and pick the d that minimizes, that maximizes it. It turns out to be 3 power n by 3, because this would be like, I mean, this will solve to d plus 1 power n by d plus 1. Yeah, and when d is 2, this is 3 power n by 3, and that is the maximum. Okay, that is just a informal, but you can just convert it into a formal proof of this. So, that gives me this bound, and I gave you an example where it is tight. Now, what does that mean for this algorithm? Now, if I want to find the chromatic number of an induced subgraph, look at all maximal independent sets of that, color it with one color and color the remaining recursively or from the table. So, that gives me this kind of a running time. It is not now 2 power I, it is 3 power I by 3. So, this would turn out to be 1 plus 3 power 1 by 3 whole power n. So, this is roughly 2.44 power n. Okay, so, essentially dynamic programming plus the observation that you can the number of maximal independent subsets of a graph on I vertices at most 3 power I by 3. This can actually be even improved to 2 power n using inclusion exclusion. Okay. I don't want to get into that. Yeah. Currently, I think yeah, I think it's, I mean, I'm almost sure, I'm not 100% sure, but yeah, so that uses some inclusion exclusion and dynamic programming combined. Okay, I don't think I want to say much more than this. Fine. Yeah, so here are some examples of modern uses of dynamic programming. Can you find it easily? Yeah, this recurrence actually gives you a way to find it, right? Because this is a branching algorithm. I pick a vertex, any of its neighbors, so that's so many choices, and then you can find them. Okay, so one other example, let's do it. And so finding a maximum independent set in a tree. A rooted tree. Again, you wanted variety of this subproblems, right? Well, how do we guess this? Right? This is yeah. So there are actually several linear time algorithms for this. So we know maximum independence and also minimum vertex cover, right? Because these things are complement of the set complement. If you find the maximum independent set, the remaining thing is a minimum vertex cover. That's how you actually even show that these are NP complete. But in a tree, you can find this in polynomial time. Okay, this is one very simple algorithm. I'll tell you that first for minimum vertex cover, and hence you can also get that algorithm for maximum independent set. And then I will actually tell you the dynamic programming, because dynamic programming is illustrative for a different purpose, because you can generalize this for not trees, but also what are called bounded tree width graphs. So for that, dynamic programming is useful, but let's give a simple algorithm for minimum vertex cover in a tree. Okay. So what? So if I have a vertex which is a degree 1 vertex. First of all, I assume tree there is no degree 0 vertex. If you have a degree 1 vertex, then can you suggest sort of a simple way of handling degree 1 vertices? Just remove that and that's it. Pick y, because you have to cover this edge, right? I can't just delete it. Yeah, exactly. No, you just said delete it. Just deleting it is not enough. Delete it and include name y. Yeah, that's what everybody is saying, right? So one simple way of handling degree 1 vertex is just you can prove it that exactly the way you are saying, that if I anyway somebody has to be picked, x or y, to cover this edge, and y will do more things. So if you have an optimum solution which does not include y, then it must include x, because to cover this edge, you throw away x and put in y, you will do as good a job. And I mean, it doesn't, the size doesn't change, and it's also a vertex cover. So there is always an optimum solution that includes y. Okay, you need this 3-line argument to show that there is always an optimum solution that includes y. So safely we just include y and delete x and delete all its neighbors. Now suppose I keep doing this, what happens in a tree? Yeah, well, that will also be a degree 1 vertex or whatever. You will be done, right? That's it. So that's a polynomial time, and you can actually implement in linear time algorithm to find the minimum vertex cover in a tree. All you have to do is to find a leaf. You know, tree always has a degree 1 vertex, at least 2 of them. So, just go pick its neighbor, delete it, find a degree 1 vertex, pick its neighbor, delete it, keep going, keep going, keep going. And whenever along the process, if you have isolated vertices, delete them as well, right, because isolated vertices are no use. So, this gives you a clean simple algorithm for minimum vertex cover in a tree, and hence also for maximum independence. Yeah. In between, you might get isolated vertices, because I might get something like this. So, you pick this and delete it. So, these guys become isolated, right. Delete isolated vertices, keep going, and you will actually find the optimum vertex cover for a tree, and hence maximum independence. But we will actually give a dynamic programming algorithm, because as I said, it's illustrative it's useful to generalize this for bounded tree with graphs and so on, about which we probably won't get in. So, it's a rooted tree. So, now let us do some choices, right. What's the choice you want to make? So, you have a rooted tree. So, that is how your tree looks like. Okay. So, let us make a choice. What are the sub problems we want, right? And the first thing we want to figure out is do your choices and see whether what sub problems you want. So, what is the choice you want to make? Root is in my solution or not? Let us do that, right. So, if root is in a solution, then so one other just observation is that many of this also generalize for weighted versions also. If you look at the set cover, I could have sets having weights, and I want to find the minimum weight family that covers the entire universe. Pretty much everything goes through, right, because when I was doing this dynamic programming, I said either the last one is in the solution or not. If it is in the solution, I added 1. Instead, you should add the weight of that set, right. So, that is the only difference, otherwise it works through. So, even here, for example, I can have nodes having weights, and I can find the maximum weight independent set. Okay. So, if root is in the solution, then so I include it in my solution. Then what is the recursive subproblem? All its children, that subtree. So, in that, so when you have these subtrees where you want to find somehow recursively solutions, right, but okay. So, then because if you, so then it is the root is in the solution. Okay. So, let us talk about MAS of T, right, maximum independence of this tree. I am looking at the root, okay, with root is equal to 1 plus MAS of T1 or maximum of, no, is it maximum of, sum of, right. I am looking for a maximum independence set. These are independent sub problems. There are no edges across, that is a nice thing. So, you find a maximum independence set here, maximum independence set, maximum independence set, add them all, right. So, that is a sum. Ti, where Ti is a subtree of root. Right, but you also said some other condition. It is not just maximum independence set, because yeah, with the condition that root not in solution. So, sort of you are putting this condition in there because you picked this and you are looking for independent set, none of this must be there, right. And if root is not in, just a sum of the no condition, right, then it is just sum MIS Ti I Ti is a child. I do not know whether root is in or not. So, you pick the maximum of this, right, because you are talking about maximum thing. So, what are the sub problems now we want? Not just sub problem is not subtrees with this extra condition, right, agreed. So, sub problems are you want find maximum independent set on the subtrees. So, the way you will actually do it is do some post order traversal on the leaves, it will be easy and you go up. Okay. So, that is the order in which you will compute them. But the important thing is this extra condition. So, let us create that many sub problems, right. For every node, I will have 2 sub problems. Find the maximum independent set of the subtree with the condition that root is not there or without any condition. Okay. So, okay. So, let us call E of t is the max size of MIS of subtree, or this is a node, subtree rooted at x such that x is not in the MIS. And let us call M of x is the size of two quantities. Okay. Now, we need to compute both these quantities at the root. In fact, we need to compute both these quantities at every node. We will write a recursive formulation and then we are all set, right. So, what is E of x? That the size of maximum independent set at x such that x is not in this solution is simply summation m of xi, xi is a child of x. Agreed? So, if you tell me that x is not in the solution, then I go to all my children, find the maximum independent set, no conditions. So, that is m and add them all. So, E of x is this. What is m of x? No condition. One plus summation E of xi, because I include it in the root. That means that I have to do but I could or Ex. or a max of. So, either exclude the root and find the maximum independent set, or include the root and find that forces you to this. This is it now, and so my goal is to find m of x. Yeah, you could also say I of x, the size of the root tree with I am forced to include x, then I pick the maximum of the two, but this is with no condition. So, now what I really want, what is my goal output? M of the root, right? And what is sort of the base case at the leaves node? If x is a leaf, then Ex is 0 and Mx is 1. Size of the maximum independent set in that subtree. That is it. So, now you do a post order traversal of the tree, somehow going from the leaves. And so, when you get to a node, you know everything about this node. You know the Mx and Ex, you know Mx and Ex of this subtree. So, now you can use this formula to compute. So, it is a constant time, well no, sum of the degrees basically. So, if you are at a node, how much time does it take to compute your value? If you have computed for your children, it is a sum of the degree, it is just a degree. That means how many child I have, because it is here is a sum and here is a sum and the max and so on. So, sum of the degrees, what is the sum of the degrees in a tree? It's 2n. So, it is a linear, overall it is a linear time. So, you just go from bottom up. So, you are computing two. So, the sub problem tells you need to compute two things, some generalization, always some generalization, and including, excluding. And for bounded tree with graph, you will actually compute many things at every intermediate node. So, here you are computing two. So, there is a notion of bounded tree width, you will get to it sometime later next semester or some other course, where these are actually some separator sizes. So, it might have some k size separators. So, you will try all possible combinations of them, for which you compute maximum independent set, then you carry this over to the root all the way. So, overall this is okay. I think we will stop and we will see some more examples on Thursday.